evening. In fact, it's late in the night. I think it's 3 hours of the morning, 1:30. Okay. So yeah, those of you who are new to the channel, kindly subscribe it and please watch the previous video because we will be sorry doing a problem on gain margin and phase margin. So let's go about the problem. So there's a expression g of s, h of s. Okay, this is in time domain format wherein it's written as s plus 1 s plus 1 by 2. Here we require what we'll be doing is that we need to find out its basically the gain margin and the phase margin. Okay, and in order to get the gain margin and the phase margin, it's mentioned that the gain crossover frequency, gain crossover frequency here it is given as 0.82 radians per second. So whenever you are solving this problem, you please make sure that you keep the calculator in the radian mode, not in the degree mode. So as you know the gain margin definition, first of all you have to express this in terms of S. You have to replace this value of S as j omega, okay? So, and you can write straight away minus 20 log of 10, okay? And this is g j omega h j omega, and what is the frequency? And the value of omega should be equal to omega gc. That would be, that is already mentioned here, is 0.82 radians per second. Now, in order to get this, basically the gain margin definition, which we have seen that it's the margin in the previous lecture. Those of you have not seen, please visit the previous lecture. It's the margin basically allowable by which gain can be increased in the system reaches the verge of instability. And similarly, so here I can express this term in term of see 1 by 2. So this can be written as 1 by, for gain margin, this can be written as 1 by s can be written as 1 by omega. Okay, 1 by j omega. S should be replaced by j omega, and this is j omega plus 1. Okay, here, and this is zero point 0.5 plus j omega. Okay, and now if you want the value of this system, okay, so what you need to do is that this j omega value needs to be rationalized, and the imaginary and part should be set to 0. So you'll get the value of the gain margin. So how do you go about rationalizing this? So you take this, you multiply this term by into minus j omega, okay, 1 minus j omega and zero point 0.5 minus j omega. So this is the rationalization factor. Here also you have to minus the same thing, 1 minus j omega, zero point 0.5 minus j omega. So basically this is like, see, if this is a this is okay. So this is b term, this is c term. So you can get, see, this you can write as if you multiply this on both the sides, so you'll get as, so leave about this. So this is a, this is b, and this is again a, and this is b. So this is a plus b, a minus b. So this will become a square minus b square. Okay, a plus, and similarly here also this will become, forget about this a and b. This is confusing. So this is in the form of a plus b, and this is in the form of a minus b. Same here. This is a plus b. This is in the form of a minus b. So this is what rationalization would do. So j omega and j omega will become minus j square omega square. Minus j square is nothing but as 1. So directly you can write in the down omega square, and that value is like, okay, a square minus b square. So minus of j square is again 1, so it is 1 plus omega square. Similarly there also 0.25, and minus of j square is 1, so it will be 0.25 plus omega square, and on top the same thing will remain, that is minus j omega, 1 minus j omega, zero point 0.5 minus j omega, same thing is remaining. And now once you have done with this, you can rationalize it. Okay, after rationalizing this, it's a very simple procedure. Okay, you directly go for the rationalization process. And let this, what is happening here, I'm sorry, just got disconnected. Yeah, now it has come back. So after rationalizing this factor, you arrive at this j omega 0.5 minus omega square. This is a simple, okay, and with, in the denominator, this part, let me don't repeat, this is the denominator part, and you can segregate these sections, and you can, okay, take the imaginary part and equate it to zero. Equate it to zero. So the imaginary point part is only imaginary part here. Yeah, what happened from current slide? So the imaginary part here is only zero point 0.5 g omega. Okay, so you can equate this zero point 0.5 g omega, that zero point 0.5 sorry, zero point 0.5 minus omega square, and you can equate it to zero. So you get a frequency, and you put the value of omega, okay, here. That value is for that 0.82 radians per second. So once you have put this value here, okay, so you get the value of, sorry, you get the value of omega as omega would be equal to zero point 0.5 square under root of zero point 0.5. So you get around 0.7071. So now this is the phase crossover frequency. You are yet to get the gain margin. Okay, this is the phase crossover frequency, that is 0.7071. Now in order to get the gain margin, okay, I'll change the slide. In order to get the gain margin, you have to write for the gain margin, that is your minus 20 log of, okay, you write in that form. 1 by s would be omega, and the magnitude of the second term was 1 by 1 s plus 1, it would be 1 plus omega square, and the third term was would be 0.25 plus omega square, because 1 by 2 was zero point 0.5, so 0.5 का square हो गया 0.25, and the phase crossover frequency you have calculated as 0.7071. Put this value of omega here, you will get the value as, okay, you will get the value as minus 20 log of this value would, this entire value will get reduced to 1.33. 1.33. So if you calculate this in your calculator, you get 0.2498 dB. Okay. Now you see the gain margin is negative. Gain margin is negative. You can say system is unstable. I have already told you it has to be positive for stability. Now let's check for the phase margin. So phase margin, if you have not watched my previous video, please go and watch there. So phase margin is 180 degree plus the angle of gj omega and hj omega. And what is gj omega, hj omega? So gj omega, hj omega angle would have been, see, 1 by j omega is 90 degrees. Then 1 plus j omega, term 1 plus j omega would be, see, 1 plus j omega would be tan inverse of omega. Then we have 0.5, 0.5 plus j omega. So it is simple in tan inverse of imaginary by real. Imaginary by real. So the first term 1 by j itself, 1 by j itself means minus 90 degrees. Okay. So this is angle, first angle is your 180 degree. The first angle due to the contribution due to this j term is minus 90 degree. Then the second term 1 plus j omega is tan inverse of imaginary by layer. Tan inverse of imaginary is omega by 1. So this is minus tan inverse of omega. Okay, minus tan inverse of omega is the contribution due to this angle. Okay, then the left part is this. This is what is the imaginary here, minus tan inverse of omega divided by 0.5. So minus tan inverse of omega. So this is minus tan inverse of omega divided by 0.5. So omega value, they have mentioned the phase crossover frequency. Sorry, the gain crossover frequency omega GC they have already mentioned, that is equal to 0.82 radians per second. 82 radians per second. Substitute this value here for the value of omega, and you are going to get these values: 180 degree minus 90 minus 39.35 minus 58.62 degrees, and the final calculation you get minus 7.97 degrees. So this is the value of your phase margin. Now you can see both your gain margin is negative, your value of phase margin is negative, so it can be set the system. Gain margin is negative, phase margin is also negative, so system is unstable. So this is system is unstable. This is how a problem on gain margin and phase margin can determine the stability of the system. Hope you have understood this lecture. So we'll be stopping here. Thanks a lot. Okay, those who are new, kindly subscribe to the channel.